Good morning, everyone, and thank you again for taking the time to attend this session. As Holly's already introduced, my name is Mark Dennis. I work for Systems and Network Training in the UK and have been a professional in data networking for a good part of my professional working life. So yes, we've done many of these training sessions together. The subject of this webinar, as you can see here, is peering and BGP buzzwords. So as we can see here, that's what we're going to be looking today. So BGP in the internet is now 30 years old. It's very well understood. And now the internet is very much dependent upon it for ensuring that your messages used by your applications get to where they need to go. Now, personnel involved in engineering the internet will no doubt be aware and may use the terminology and buzzwords surrounding BGP in everyday conversation. But if you're not that close to the engineering side of things, then perhaps the technical jargon can be somewhat bewildering. So this then is a 2-hour webinar on the subject of peering and BGP buzzwords, which is not that easy to say, and with the goal of making the BGP industry jargon more understandable outside of perhaps a purely technical audience. So I understand there's a mix of people in the webinar today, and I suppose I've toned the presentation to be more acceptable perhaps to a less technical audience, but nevertheless one that's still interested in and involved in internet technology. So this webinar provides simple yet comprehensive explanations of common terms used by the internet community, including and involving the use of BGP. If you don't understand some of the terms surrounding BGP, then please stay. I will be explaining them. And again, just a reminder, quick, please do use the buttons for Q&A, and Holly will take the questions. We'll be taking a break at about 55 minutes from now for 10 minutes, and we'll be answering your questions at the start of the next session and at the end of the next session as well. Now, I put up an objective slide here just to kind of set the tone. I guess I've already introduced this, but you know, what we're really doing here is looking at BGP terminology. And my goal really is to try and visualize what we mean by these terms, show how and where these terms apply to the function of BGP. So hopefully you'll go away from this session a bit more knowledgeable and able to have conversations regarding BGP and peering in the internet. That's my goal. So without further ado, let's start our conversation and do some BGP buzzword bingo, if you like. So in this session, we'll start with the basics. We'll first start with examining what BGP is itself, and then as the presentation unfolds, we'll be doing a sort of what's what of BGP related terms. Now, if you're not from a particularly technical background, then it's probably worth stating that the secret sauce, if you will, of the internet today is that all network connecting equipment shares a common standardized internet protocol addressing scheme, that's IP, and a globally scalable border gateway protocol, that's BGP, to route your packets. And these together enable the networks of the internet to interconnect with each other, and we can use the internet with our applications to send data messages, data packets, all sorts of stuff across this interconnected network. So again, what I hope to do here is start with BGP and then go through a discussion of all of these buzzwords that I'm putting up here. And we're going to divide this into two halves, as I say, because that's quite a lot to digest in one go, and provide examples for each of these to help you to digest and hopefully remember the context and the meaning of each of these buzzwords that we've got on here today. So I did a little bit of research, and after doing some searching, just found what I just kind of concluded were the top terms to use in the context of this presentation today. So hopefully these will hit the mark, and I can help you to understand what these terms in a more meaningful way. So let's get started then. And we start with BGP itself. And so if we ask ourselves, what is BGP? BGP is really nothing more than an application. So it's an application, just the same as, you have applications on your phones, on your laptops, on your computer systems, but it's an application specifically that runs on network routers. And if you're not familiar, these kind of hockey puck type of icons on here, these are network routers. And you can see in the world, there's an awful lot of routers. So BGP is an application that runs on routers and enables the routers themselves to share information about networks. So like all applications, BGP has a language of communication between the different parties, the different routers in this case. Now, throughout the world, we have this universal ability to communicate, and that's because we're all using BGP version 4. And so in this case, all of the routers in the internet and routers in your business can intercommunicate and share information about routes because they're all using a common version. Now, it's estimated that there are actually millions of routers running BGP in the world and interconnected on the internet, and they're sort of interconnected with links in a sort of partial mesh kind of way. And so those routers, they don't all belong to one organization. They belong to different ISPs, internet service providers, large enterprises, content delivery network providers or CDNs, cloud service providers, and other private and government and educational organizations that all are participating in this collaboration of networks, which is the internet. So BGP as an application on a router is effectively a messenger. It's an application that sends messages, and those messages tell other routers about networks that they know about. And then those other routers pass on that information to other routers. And so the networks gradually get known about across our globe through the internet. That's effectively what BGP is. Now, there is a term which is used in many different contexts, but I want to just try and be very specific here. We have a term called BGP Peering. So what is BGP Peering? Well, this is fundamentally something that you do as an internet router. And I can see I've drawn routers all over the place here. So if you are an internet router, when you want to share information about routes or send messages, if you like, to another router, then you have to form a relationship with that router. Okay, you can't just send messages and hope they're going to get there. So if we take a look, for example, at this picture over here, what I'm trying to demonstrate here is that not all of the routers in the internet, as we just said, belong to a specific organization. There are many, many, many. There are tens of thousands of different organizations in the internet with their routers, and they interconnect with each other in a partial mesh. So in order for the routers, let's say, of this organization called ISP ABC to communicate with this organization, ISP, that's Internet Service Provider XYZ, then their routers must first peer with each other, and that is to create an open channel of communication between their routers. And then, and only then, can they actually pass routes to each other. And the relationship that exists between this ISP's router and this ISP's router is bidirectional in nature. So ISPs must use these BGP sessions to send and receive routes. And those exchange of routes enable IP packets of data, in turn, to traverse the internet across different ISP infrastructures. No single organization, no single internet service provider, if you will, has knowledge of all networks in the internet intrinsically. So they must share routes. BGP allows route sharing from, one part of the globe to another part of the globe, one part of the country to another part of the country, across continents, etc. Share routes so that we as users, we as consumers can get access to services across the globe. So the BGP peering sessions enable that sharing of knowledge. So BGP peering is just a technical term for a communication session between BGP routers, and BGP routers are simply routers that are running this application called BGP. Okay, so, okay. 2 buzzwords down, let's carry on and see where this takes us. Now, again, we've got this same sort of graphic up here, and this could be an enterprise organization or a government organization. It could even be another service provider, and they have, as I'm indicating here, they have routers that they own and that are interconnected. And let's say this is a customer called customer 1. When that customer 1 wants to connect to the bigger, wider internet, maybe they have a contract with service provider XYZ, and service provider XYZ has its routers, as we can see here. And maybe they don't just want to use one service provider in case that service provider should fail. Maybe they want to use another one, like ISP ABC here. And so the customer connects to these service providers using their routers and using BGP peering. And then those service providers connect to other service providers up into, the sort of the core of the internet, if you like. And we'll talk a little bit about that. Now, question, how does BGP know which organization is passing it routes? Okay, so if I'm a customer here and I connect to the service provider here, of course, initially someone from this organization is going to have a conversation with someone from the service provider up here, or this service provider over here. So at a corporate level, we know kind of, who we're talking to, and we're going to set up this peering, this relationship. But how does the router itself know? So the BGP application that's running on these routers is not smart enough to know that, when it peers with this router here, it's peering with ISP ABC, or this one with ISP XYZ. There's nothing in the BGP application that mentions organizational name. And after all, bad routes could mess things up. So-called poison routing information could certainly be a threat to, this company's ability to be online, or for this service provider here. If it's got bad routes, it's not able to connect its customers to the internet. Well, as a first kind of step in route identification, an organization is said to group its routers into something called an autonomous system. So an autonomous system is a grouping of routers within a given organization. And each organization must register its autonomous system with an internet registry, such as RIPE or one of these other internet registries, depending on what region you're in. And upon doing that registration, the organization will receive a unique 32-bit autonomous system number. So ASN stands for autonomous system number. So its routers, if you like, will be labeled with that autonomous system number. Now, I've greatly simplified this here just to make it easy on a slide, and I've called this service provider's routers autonomous system A, this one's B, C, D, etc., like this. And now, when routes are exchanged, the autonomous system number of the advertising router is included in that advertisement. So, for example, if ISP ABC is peering with the ASNB over here, when ASNB or ISP XYZ advertises its routes, then the routers in ISP ABC will see them as coming from ASNB. So the autonomous system number provides a sort of rudimentary identification, if you like, for a given organization's routes, so that they can be advertised and they can be seen as in the internet, and we can see who routes are being advertised from. Now, these autonomous system numbers are issued by these 5 internet registries, as I said here, and there are actually, you have to register, like I mentioned before, your autonomous system. Over 100,000 of these autonomous systems have been registered with the registries, although that's a huge number, although there's about 30,000 odd ASNs actually seen in the internet. So when we look at the internet and we can see who's advertising those routes, that number's about 30,000. So many more have been registered, but about 30,000 is what we'll see in the internet today. Well, that's still a very, very large number. 30,000 of these clouds, if you will. So just extending this conversation a little bit further to have a look at some more terminology here. We have something called a BGP speaker and a BGP neighbor. So firstly, with respect to the term BGP neighbors, what do we mean by that? Well, where we have a peer session between BGP routers, such as here between A and D, or between C and D over here. In this case, these letters refer to the name of the router themselves. So if routers A and E are peering with each other, then we call those routers peering with each other, we call them neighbors. Okay, so BGP routers that are peering are neighbors, and therefore neighbors can send each other routes. Now, when a router communicates with another router over a BGP peering session, It's sometimes referred to as a BGP speaker. So here, for example, router D is sending some routes to its peer or neighbor C. And so we say that router D is the BGP speaker. It's the one sending the message. Remember, BGP is a messaging application. And so the speaker is the one sending that information. And another buzzword here, if you ever hear the term update, okay, an update, when a BGP speaker sends to its peer or neighbor an update, okay, and the update is going to contain one or more routes, some routing information. So D is sharing with C some information about routes that it knows about, so C can get that information. Okay, so in that case, what would happen here is if D is sending some routes to C, now the organization, ABC, that has router C will learn about those routes and get access to whatever service are behind those routes, whatever, you know, is it a website, is it some sort of email service, storage service, whatever. The routers are sharing information about routes in their update, and that means that routers can send packets towards those routes and use those facilities that are on the internet. So an update is a packet sent between routers and contains more than one route. It's only going to happen if these routers are neighbors, and the update is sent by what we call the BGP speaker. Yeah? So pretty straightforward. And so speaker, peer, neighbor, they're all interrelated terms, and hopefully now you've got some kind of idea of, if you hear those terms, what they refer to. Okay, we can't speak to anyone else unless we have a peering with them, and they will become a neighbor once we have that peering session set up. And then we can share routes. That's all that terminology really means. Okay. So that's got some fundamental BGP terminology kind of out of the way. Hopefully, I've made that reasonably clear. Now, BGP is nothing without IP, the Internet Protocol that we mentioned before. So, you know, these routes, if you like, that are being shared in updates, those routes are all based on this other terminology of IP and IP addressing. So I want to try and make this sort of fairly straightforward to understand. So let's go and have a look at IP and IP addressing, and we can put this in the context of what BGP is doing for IP and IP addressing. Devices on the internet have a unique address. That will be an IP version 4 address, or an IP version 6 address, or these days devices are what we call dual stack, which means they have both an IP version 4 address, which looks like this, and we say 192.168.1.1. Okay, that'll be an address that, you know, you'll have on your phone, your laptop, etc., and it'll look something like that. It's made up, of course, you know, it's digital at the back end, so it's actually made up of bits. There's actually a bit representation here. I'm not going to ask you to remember that, but that's a bit representation of this number. There are 32 bits in total there, okay? And that's what an IP version 4 address looks like. It is reasonable for humans to remember an address like this. On the other hand, an IP version 6 address looks like this. which is made up of 128 bits. And I can't put those 128 bits on my slide, so you're not going to get them, unfortunately. But this number here is represented by 128 bits in the same way that this number is represented by 32 bits here, if it's an IP4 address. And we can't remember this. It's virtually impossible to remember this for humans, but that is nevertheless what it looks like. Now, the reason we have that complicated address, of course, is because the IP4 addresses have been depleted from the internet registries that issue them. And so IP version 6 provides a much more scalable addressing scheme to provide every device on the internet with a unique address for the future. And it's much more scalable, of course, because it has more bits. The more bits you have in an address, then the more combinations you have, therefore the more numbers that you have. Now, interesting for BGP, routers and BGP are not really interested in these specific addresses. They're only really interested in part of these addresses, okay? And the part of the address that they're interested in is called a prefix. So for version 4 addresses and version 6 addresses, there is a part of that address which is the prefix. And this is the part of the address that tells everyone, including routers, what IP network those addresses belong to. So groups of devices can belong to the same IP network. On the internet, their addresses must be unique, but you can have multiple addresses belonging to the same IP network. In other words, you could have multiple devices, either IP4 or IP version 6, that share a prefix. And the prefix identifies the network that they can belong to. These prefixes, of course, these networks must be unique. And these prefixes are what BGP advertises when it sends updates, when the speakers send updates to their neighbors. So we're going to have a look at what prefixes are. They must be unique in the internet. The prefix must be unique because if you have a duplicate network, then the router is going to get confused as to, well, which of those prefixes do I send them to? If I've got a packet to be delivered across the network for a given application. If there are if there are a duplication of prefixes in different parts of the world, which one do I send the packet to? So prefixes are unique. They represent a network number, and they represent the network where all of our devices that connect to the network belong. So how can we go from an address here to a prefix? How can we know the prefix that a device belongs to? Well, we use something called a mask. And I'm going to explain masks to you via which I hope will be a very simple demonstration. So here I use the example of a postal address on an envelope that gets a letter to where it wants to go. And the apparatus that gets the letter to where it wants to go is the postal service itself. Okay, so we can think of, let's say, the address as what is written on the envelope, and we can think of the mechanics of getting that envelope to where it needs to go as the postal service. So in our IP world, we can think of this address as our IP address, and we can think of the postal service as the internet. In other words, BGP getting our packets to where they need to go. Now, in this example I've used here for the postal address, this is the address of the company I work for. And it's essentially divided into two parts. And I'm going to use a mask in the same way that we use mask with IP addresses to divide up the two parts. First of all, we have the location, which is, Bletchingley Road, Nutfield, etc., etc. This is not unique, as in, yes, the road is unique and the town is unique, but there are multiple businesses and households on this road sharing this same road address. So, effectively, there could be lots of envelopes in the postman's bag, and lots of them are going to different houses, different buildings, but they have in common the Bletchingley Road, Nutfield, Surrey, RH1, etc. So that's the first part of the address. And then the second part of the address is the actual specific building and company name. And that, of course, is unique to the company that I work for. So if we think of the address on the envelope as an IP address and the postal system as the internet, it can help us to understand how the IP address is used to deliver application data packets. Okay, so let's apply the same rules here to an IP address. So remember, the internet has to deliver packets of data on behalf of user applications to the correct network. And this is what the prefix is used for. If there's a duplicate, then the routers don't know which one the packet should be sent to. So how can we know the prefix that a device belongs to from its IP address? Well, again, we'll use this mask. And the mask tells the sending device and the routers which network the packet that they have to deliver belongs to, or which network it's destined for, which is, as we said before, the prefix. So let's take a look at this. So if we were to add the mask to our IP address as before, it now looks a little bit different. It now looks as 192 and 168. Now, in IP addresses, by convention, what we have to do is where the mask is covering part of the address, we have to add zeros here. And we also have to say how big the mask is. Well, if it's 32 bits for all of this, and we've covered half of it, the mask is 16 bits. So by adding the mask and putting zeros here, we end up, and then saying how big the mask is, we end up with something that looks like this: 192.168.00, and then a slash, which is the notation, and then the number of bits in the mask, which is 16. This then is, by using a mask of 16 bits, this is the prefix, or this is the network that this address lives on. This is the street and town, if you like, that this address lives on. And that is what your router with BGP is going to advertise. Okay, we can do exactly the same thing with our IP version 6 address. If we put a mask over the address, which is half the address, it's 64 bits of mask. In IP version 6, by convention, we have to put a double colon where we cover a bit of the address. And then we state how many bits the mask is in size. And we end up with an IP version 6 prefix, which is now just this bit here, 2001, etc., 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 up to this point here. That's what we can see here. And then double colon, and then 64 for the size of the mask. That is the network part of the address, or the prefix part of the address, that IP version 6 IP lives on. That's the street, in other words. The bit behind the mask that we're covering up here, that's the bit which is the actual specific address of a particular device. The bit that we're left with that you can see, that's the prefix. So if your BGP router is advertising your IP version 6 prefix to tell everyone where your network is, tell routers where your network is. That's what the BGP router is going to advertise, that prefix there. Okay, so that's the relationship effectively between IP and BGP. We create IP addresses for everything to uniquely address devices. We can calculate their prefix based on a mask, and then we use the BGP router to advertise those prefixes so that effectively, routers distribute information about the street and town that the devices on the internet live in effectively in IP terms, both IP version 4 and IP version 6. So what's a BGP root? And how is it different from a prefix? Well, it's fairly straightforward. So I'm being a little bit simplistic here, but basically the root is a combination of the prefix plus the router ID that's advertising the route to another router. So let's say, for example, here, this router B is advertising this prefix here to router C. So router C receives the route and it sees, which is this part here, and it sees who's sending it. Okay, the address of the sending router, the IP address of this BGP router here. And we call that the next hop. So in other words, when you receive a router from a speaker, from your peer, it's going to be one of these prefixes, and it's going to be also, you're also going to see who is sending you that. So we have a next hop here. And what that means is, if C wants to know how to get to or send a packet to something on this network here, then it just has to send it to the next hop. It sends it back to B. B is advertising a network to C, so C can send packets to the network where devices live. If C gets a packet to anything on this network, it knows it can forward that packet to B because B advertised that network to it. And you can go further and say, well, okay, let's say C passes that prefix here onto this router in another ISP, router X. If X gets a packet for a device on this network, then where's X going to send the packet to? Well, it's going to send it to its next hop, and its next hop is C, because C was the router advertising that route to X. And so X sends to C, C sends to B, and the packet gets to the network where it's intended. And that basically is what is happening across the internet. That is what BGP peering allows, and BGP speakers with routing updates sending these prefixes allow to take place on the internet. So hopefully, all this, kind of BGP, I obviously created, a simplistic model, but this is the fundamental mechanics of BGP and how it relates to the roots, and how those roots are basically prefixes, and how those prefixes are effectively announcements of networks that our devices with their applications sit on. And by the use of those, distribution of those routes with BGP in the internet, our packets, our application data packets can hop from, one ISP, if you like, to another, to get to their destination network on the internet. Continuing with our buzzword bingo, if you like, though, there's another term that's used in the context of what we've been speaking about, another buzzword, if you will, that can be a little bit confusing. So if you encounter the term CIDR, okay, which stands for, and this is perhaps not even, doesn't make it any clearer, classless inter-domain routing. What's this all about? Now, the technical folks will kind of understand what this means, but if you're not from a technical background, then, well, really, all this means is exactly what we were just talking about. Okay, for any IP address, we can add a mask of a given length to create a prefix. Okay, we can take an IP address, we can add a mask of a given length, of a specific length. We can use various different masks of different lengths. I've used the same example here of 16 bits. And that's going to create a prefix. And the prefix can then be used for routing. Okay, the fact that we can use different size masks is what is the reason for the class list there. But what we just did, that illustration of what we just did before, that is what classless interdomain routing means at its at its most essential. So so yeah, that's another one of those buzzwords. That's what CiDR is. Now, we've talked about BGP and how it exchanges routes, and we can see these routes using various pieces of monitoring equipment in the internet. One such monitoring tool is something called a looking glass, such as, for example, what we're seeing here is the looking glass of the London Internet Exchange, LINX. And we can see a number of different prefixes here and their next hops, or in other words, who's announcing those prefixes. In this case, we can see that this is the IP address of a router, and it's advertising this prefix and this prefix and this prefix, etc. I'm just going to jump over to this site here, okay, which is also the London Internet Exchange. And here we can see a number of these autonomous systems. There's 42, 917, 983, etc. And the ISP or organization that those autonomous systems belong to, and the IP address of the router that's basically sending out routes from these different autonomous systems. So the top one here, Packet Clearinghouse, is autonomous system 42. That's the IP address of the router, and it's sending and receiving 85 routes here. And if we click that link, we see the page that I just showed on the slide. There's a list here of those 85 different routes that are being advertised across the internet from that AS42, from the router with this address here. So there's multiple different tools that we have. Looking Glass is just one of them to enable us to see the activity of routes being advertised in the internet for sort of monitoring purposes. There are tools such as route collectors, which are other monitoring device. LINX has route collectors. There are route collectors in the internet exchanges as well. There's something called route views. There are multiple of these devices throughout the internet. And when they view those routes, as we just saw listed, they sort of classify them into 3 different categories. So I want you to imagine the internet here in a sort of an edge and core way. So towards the edge, we have, basically customers' equipment and customer routers, like we see here, that have their own autonomous system. And then they connect to internet service providers here with their routers. And these autonomous systems are said to be upstream of the customer. Upstream being towards the internet, with the customer at the edge, and then the interconnecting internet, going further and further towards the core. And these service providers have an upstream service provider here. Now, when the root collectors examine routes, so when an upstream service provider with a root collector is looking at its customer route, so let's imagine here ISP XYZ has a monitoring root collector in here, and it's looking at downstream customer networks being advertised. The customer is advertising its network so that people on the internet can get access to the customer's devices on their networks. Those sort of routes are called customer or customer cone routes. If we are a downstream customer or a service provider here, and we have BGP peering with an upstream internet service provider like so, and this upstream internet service provider is advertising routes from the core of the internet downstream to us, or if we're peering over here with another service provider at the same kind of level, if you like, then these routes are seen to be external routes. And the route classifier will classify these routes accordingly. So we have these different types of routes. Finally, there are internal routes. We don't normally advertise these. These would be routes that are specific to the internal workings of a service provider, and they wouldn't necessarily be advertised out, and they wouldn't necessarily be something that a route collector can pick up. But there are these other types of routes which are smaller in number. So there is a classification of routes, in other words, is what I wanted to show you. If you add all the routes up in total, we can see from the internet, we can see that the numbers of these prefixes or routes that the routers have. And in the case of IP version 6 routes, those routes have been steadily growing from, this figure here shows, and this is Asia Pacific Internet Registry, a blog that they wrote, shown steady growth, and it's increasing at about 26,000 prefixes are added to their routers per year. And so you can, the conclusion of this blog is that they expect to see that number increasing at a similar rate, for the foreseeable future. In terms of the IP version 4 routes, that's a much bigger number, but the number is really kind of tapering off here. So these are those prefixes that are seen in total in the internet from tools like root collectors, for example, and there are a cumulative number of what we're seeing in the internet. What this blog is saying is that they expect the total number of IP version 4 routes, to level off at just over 1 million by around 2029. They can't tell exactly for sure, but that's the the best estimate so far. And then finally, just to wrap up this half, if that's the number of kind of routes that are being sent through BGP peerings across the internet in total, then how about, what sort of density or what sort of scale is involved in service providers when they do peer with other organizations? So there is this organization here called CiDR, which have again used their own thing called an archipelago measurement infrastructure, as well as root collectors from the Root Views project and RIPE NCC to look at the top BGP peering ISPs across the globe. And you can see here that the very top here is level 3, their particular AS number, and they have multiple ASs, but their particular AS of 3356, they have a cone size. This is not roots, but ASs. They have over 50,000 other ISPs or other ASs that their BGP routers in this AS are peering with. So, you know, they're obviously a huge number. They're a top tier ISP, and they are scaling to an enormous number, or, you know, more than 50,000 customers are subscribing to their internet connectivity services. And so that really brings us to the end of the first half, and time for us to take a short break of 10 minutes. Okay, thanks ever so much, Polly. Okay, welcome back, everyone, from our short break. We're going to go into the second half, and let's see how we're doing. Well, everything was blue when we started, and the orange terms, we've gone through quite a few buzzwords here. As you can see, all these ones we have effectively ticked off on our journey through BGP buzzword progress. Okay, let's move into the second half then. And again, the idea is to illustrate what the next terms will be, the ones in blue here, what they mean, help you to understand what they mean, and with examples that hopefully make sense to you. So we're going to start off by looking at these terms, transits and peers. Now, I should first, of course, qualify this one. So we've talked about BGP peering and BGP peers, and that's a very sort of a technical thing. We know it means that there is a session of communication between BGP neighbor routers so that they can talk to each other. That's not what we're talking about here. So again, I did mention this before, but the term peer obviously gets used in the general sense in multiple contexts, and it also gets used in the world of internet as well in multiple contexts. So we're going to talk about a slightly different context for peering here. So there's BGP peers, and now there's this new one as well. And we're going to talk about this together with transits. So the internet is made up of multiple service providers of different shapes and sizes. And there are two commercial service options available when it comes to ISPs connecting to each other over the internet. So I haven't specifically drawn any routers on here, but of course, it is routers that are having communication links. But what we're really specifically talking about here with transits and peers are commercial relationships between these providers. So here we can see different providers. There's a big blue one up here. There are smaller orange ones here, and there are even smaller gray ones down here. And in the same way that we were talking about different types of routes earlier, with kind of upstream and downstream, where upstream is towards the core of the internet, and downstream is towards the edge of the internet, where you know, things get connected. Then we're doing a similar sort of thing here. So this large ISP here, Internet Service Provider, is nearer to the core of internet connectivity, and these ones out here are gradually getting smaller and getting towards the edge of the internet connectivity. Now, the size of internet service providers is relevant. Larger ISPs have a larger geography and are larger numbers of customer connections and BGP peering. So we saw level 3, for example, earlier with one of their ASs, and they had 50,000 ISPs connecting to them. So if this was level 3, there would be 50,000 of these, orange clouds here. Orange, these all being a different autonomous system. So the size does vary. Now, ISPs can purchase a transit service, a commercial transit service from an upstream service provider, so that they can get access to the core of connectivity, if you like, in the internet. So, for example, here, this orange service provider can purchase a transit service from the blue ISP, and if the blue ISP has much more connectivity, knows about many more routes than this service provider, then this service provider, the one that's being paid the money, gives this smaller provider access to that large number of routes. The closer you get to the core of the internet, effectively the more routes you have access to. And if someone wants to get access to those, like a smaller service provider down here, then they pay you for that. And they pay you for transiting your service provider's infrastructure to get access to those routes. So that's really what we mean by transit here, is your a provider or a customer or whatever it is purchasing access to a large part of the internet by paying an upstream service provider. Now, as well as transit, there is this thing called a peering commercial relationship. And a peering commercial relationship might be something like, in terms of connectivity, might be something like what we have here between these two orange providers. So this orange provider can have a transit relationship with this provider here to get access to the bigger internet, but maybe it can have a peering relationship here with this provider that's on a kind of a similar lateral level to it. So that's different, and we'll explain the difference in just a second, and what that really means when you have these two different relationships, and why, as a service provider, you would probably have a mix of both transit and peer relationships with the other ASs that we've got these BGP relationships with. It's all about route sharing. It's all about getting access to the internet. And there are these fundamental two commercial relationships that have a different capability and are used in different circumstances between autonomous systems when they become neighbors with each other. And it's usually about cost and performance, and basically fine-tuning from a commercial point of view to keep your costs down and get best value for money for you as a service provider. Now, as I say, the closer that ISP routers are, or an ISP is, to the inner core of the network, the more routes are known by the routers of that ISP. So ISPs, if you like this blue one up here, have access to all of the prefixes, all of the routes in the internet, you know, that sort of million odd that we saw earlier, both IP version 4 and IP version 6. As you move towards the edges of the internet, then the routes that are known by your routers are a partial component of the total internet routes, of that total, you know, 1 million, etc. And so effectively, if this orange service provider has a transit relationship with this bigger blue provider here, if the orange provider doesn't have a given prefix in its routers and it receives a packet for a network that its routers don't specifically know about because it hasn't received or it doesn't know about a given route, then what the routers in this smaller service provider are going to do is they're going to default to a sort of or revert to a default behavior and say, well, I don't know what to do with this packet. I'm going to send it upstream to this bigger service provider because I've got a transit relationship with that bigger service provider. And because it is a bigger service provider, I know that they have all the internet prefixes and they will know what to do with this packet. They have routing information about the network, the prefix that this packet should be going towards. And so they do something which is called default routing, which basically means where there are holes in the knowledge of prefixes of these smaller providers, they send the packet upstream, of course, providing that they have purchased a transit relationship with an upstream service provider. And, you know, the general term for that is like default routing. We pass the packets upstream. Now, so default routes exist, this default routing behavior exists, you know, out from the core of the internet. It exists further out here. So this service provider will probably send upstream when it doesn't know what to do with a packet to its transit provider. So the orange is acting as a transit provider to the gray small edge provider down here. And if the orange provider still doesn't have a route, it will send upstream to its transit provider. So gray is paying orange, orange is paying blue, and the packets get forwarded to blue because blue knows about all of the routes of the internet. And there is a term for the part of the internet, the service providers and the routers of those providers and ASs in the kind of core, if you like, of the internet, where all routes are known. And it's called the default free zone. So providers that are part of the default free zone, they do not pay to any upstream provider of them. They do something else, which we'll take a look at in just a second. But there is no need for the routers here to use this default behavior because all routes are known by their routers. When a packet comes in, they will have a very large table that says, okay, if you want to get to this route, you send it in this direction. So we call that the default free zone. It's basically the core of the network. So I've introduced here transits, I've introduced peers. We're going to talk a little bit more about those now, but I've also introduced this term called the default free zone, and you should have some idea now of what that term specifically means. So let's have a look more with examples of what this transit relationship means. And transit relationships, also known sometimes as IP transit. It also can be known sometimes as rather imprecisely or perhaps inaccurately as peering point. But let's focus on the transit part of this now. So transit is a business relationship where, as I say, one ISP pays another ISP, pays an upstream ISP to get access to all internet destinations, if you like. So here, AS64512 pays 64515 because 64515 is, in the core of the internet, and it can provide 64512 with access to all destinations. So all this router needs to do is send packets up to this provider, and this provider will get them to their destination. That's effectively what transit is doing. Also, this customer down here, which is using this prefix, and it will advertise this prefix to the service provider. If this customer wants to get to something in the internet, like Google or whatever, it's going to be paying this provider for transit. So this customer pays this provider, and this provider makes some money. And then this provider that doesn't have access to the core of the internet pays this provider, and so this provider makes some money. So there's the chain of kind of commerce that goes on here. And if these two providers here, 64512 and 64513, they each have a customer down here. Okay, they're doing some, BGP neighboring down here, like so. If this customer wants to talk to this customer, then it's going to have to, in this case, use the transit relationship that this customer has with its upstream provider. And then that upstream provider exchanges routes with this provider, and then the packets can go all the way over here like so. So this prefix gets advertised this way through the upstream providers to this customer, and then this customer can send data packets there, and vice versa. So that's the packets, the actual packets will traverse this direction. You're paying a bigger service provider above you or upstream from you to get access to the internet and get access to, the customers that you want to do business with. That's transit. Now, a explanation of what we mean in a commercial sense by the peering relationship is what we can see here. So in a peering relationship, ISPs exchange routing information and network traffic for the purpose of providing access to each other's customers. Okay, so in other words, here, there's a peering relationship that takes place now, which is different to the previous slide. And that peering relationship takes place between 64512 and 64513 for the purpose of allowing their customers to interconnect over this path here, not via the upstream transit providers. Okay, now these service providers are only advertising over this link here. The BGP updates are only advertising each other's customers. I've just got one customer each side here, but of course there could be hundreds or even thousands of customers on each side, and traffic between the customers will go over this link here. Now, when these providers have a peer, decide to have this peering relationship between their BGP routers, there is no exchange of money. They're not charging each other for the benefit of using each other's networks. In other words, 64513 is not charging 64512 to get access to its customers. and 64512 is not charging 64513 to get access to its customers. The purpose of this peering is effectively to redirect, if you like, customer traffic over this link to prevent it from going up to the upstream provider. And the reason for that is that when you have a transit service, so this 64512 is got a transit service here still, because there'll be, you know, this customer will want to get out to the rest of the internet. They won't just want to talk to these customers of this provider over here. So there will be traffic going up here. But when 64512 pays its upstream provider, then the cost of the transit will depend usually on the amount of traffic going here. So if some of that traffic can be redirected across here, the amount of bandwidth that they are paying for goes down, and therefore there's a commercial benefit to 64512, and vice versa on the other side. So that's what I mean by when I say that you know, it's a balance for any service provider. It's a balance between peering relationships, which have no costs, but allow service provider here to share its customers with this provider over here. And of course, you have those relationships when it is bidirectionally meaningful for both providers to do this, and they both save, therefore, on their upstream costs that are going on here. Sometimes there are transit relationships which are fixed cost, in which case there's no real benefit of doing this, and we can go back to what we saw before. But if it's a cost which is based on, you know, the actual amount of data being used, then there's a commercial benefit for doing this. And the providers do not charge each other money for doing that. They'll just have to pay the internet exchange, for example, for providing the interconnection service of their routers. Now, worth bearing in mind here that the upstream, if these are upstream routers in the core of the internet, then they actually don't have any upstream providers themselves. They don't pay anyone, but the big top tier providers, which we'll see in just a second in another picture, they peer with each other. So if this is a top tier and this is a top tier provider, they peer with each other to effectively build out the core of the internet, and they don't charge each other for doing this peering either, in the same way that these service providers don't charge each other. But what they do charge, of course, is to their downstream providers that they are providing transit for. So as we can see here, this peering is also known as settlement-free peering because of that financial aspect. So there are kind of labels applied to the service providers, which are these tier 1, tier 2, and tier 3 levels of classification for service providers in the context of what we were just talking about with that specific example. And, you know, there are many other examples which follow a similar look and feel. So all ISPs and their ASs will belong to a tier 1 or tier 2 or tier 3 classification. At the very top, the tier 1 ISPs are effectively the backbone of the internet. They peer with each other. They have a huge geography that they cover, which can be, you know, transcontinental, multiple countries. But there's still no one single service provider that can provide you, even a tier 1 that can provide, you know, connectivity for everyone. They sort of get together as a group and they peer with each other with this non-commercial, non-charging relationship, and together they form the core of the internet, this default free zone, if you like. Okay, and they would interconnect using the facilities of internet exchanges, for example, like LINX, etc., where they can interconnect their routers to provide that backbone. They have a very high traffic volume, they have a huge customer base, and they have usually the very, very fastest links between each other. And they're made up of not just one, but multiple autonomous systems per service provider, because many of them have been an amalgamation of other service providers over the years. They build their own infrastructure, such as Atlantic internet fiber cables under the sea, and they provide internet access to effectively all other smaller providers use them as a transit. But they don't connect usually to end users directly. That's end enterprise customers. Their customers are other service providers. They own and they manage their own infrastructure, including routers and switches, which create the internet backbone, giving them really direct control over the flow of traffic across the internet. And they can therefore deliver the best network throughput across the internet backbone. They include people like Level 3, Liberty Global, Sprint, Tata, Telefonica, and a number of others. Tier 2 ISPs are a service provider that makes a combination of paid transit. So this might be a tier 2, for example, here. It could be intercontinental, but continental or a national service provider, and they would pay transit to a tier 1 provider. And they can also peer with each other as well to share each other's customer routes in the way that we described previously. They're typically regional or national providers, and there are only a few tier 2 providers that can provide connectivity for customers on more than 2 continents. Often they'll have slower access speeds than the tier 1 providers, and they are always at least one router hop away from the actual backbone of the internet. So tier 2 providers need to connect via transit, a transit relationship to a tier 1 to get access to the backbone of the internet. And of course, again, they will interconnect at internet exchange points, at internet exchanges. Vodafone, BT, for example, those are 2 tier 2 players because they do pay transit to tier 1 players. If you pay transit, then you're not a tier 1 player. If you pay another service provider for transit, then you are, by this definition anyway, a tier 2 provider. And then a tier 3 provider is a service provider that only purchases internet access via a transit relationship. That's the definition. So you will always, as a like a local or regional service provider, you will always pay another service provider for transit. You won't do any peering of your own. And tier 3 service providers, they basically focus on local business and consumer markets. They provide access to the internet for end consumer customers, like via cable or DSL or fiber, wireless, all that sort of thing. And their general coverage is limited to specific countries or even regions, like metro regions within a country. So hopefully the combination of peering in the commercial sense and transit, having explained those and then applied those to the definitions of these 3 tiers, tier 1, don't pay for transit. Tier 2, peer and pay for transit. Tier 3, only pay for transit. Then that kind of infrastructure relationship in a commercial sense and in a sort of scale sense helps to explain how these things come together. Now, we've talked a lot about, well, we've mentioned it in passing a few times now, that when ASs and service providers interconnect, they interconnect via a connectivity facility, a connection facility. And these internet connection facilities are called internet exchanges. So obviously, LINX, our sponsor here, is an internet exchange. And what that is a facility whereby if, AS's service providers, like these 5 here, we've got AS XX, YY, ZZ, YZ, and XZ, ZX rather, they want to have commercial relationships with each other, either peering or transit, whatever it is. That means that their BGP routers need to have connectivity to the BGP routers of the other organizations here. And not only do they have to have connectivity from a physical point of view, like an Ethernet point of view, but they would also have to set up peering, these relationship, BGP peering now, where we started our conversation much earlier this morning. So, and they would do that, of course, so that they can exchange routes. So the Internet Exchange Facility provider provides a very fast interconnection backbone here using Ethernet switches. And the providers, the service providers themselves, would put one or more of their routers in the Internet Exchange Facility, and they would physically interconnect using the the very fast Ethernet switches provided by the Internet Exchange provider here, which are these routers here. So that high-speed interconnection, just got 5 in my example here, but it scales to hundreds and hundreds and hundreds of service providers, or ASs, can interconnect and BGP pair with each other through these facilities. Now, there is a bit of an issue with scale, not from the point of view of bandwidth, because these internet exchanges provide a huge amount of bandwidth for high speed, low latency interconnection. That's not an issue. But the more service providers that want to BGP peer with each other, the more complex is and the higher the number of these BGP peering sessions becomes. So, for example, if we just have 5 routers here, which is a very small number, not a realistic number, there will be 10 BGP peering sessions amongst those 5 routers. And 10 is a small number, and a service provider will be able to maintain and manage that. But if there were 50 providers that want to peer with each other, that number now escalates, and there will be actually 1,225 peering sessions between the 50 routers. And the higher the number goes, it's not exponential, but it's a higher rate of increase of the number of peering sessions. And the more the peering sessions you have, the more complexity there is, the more monitoring of those peering sessions that needs to go on, and the more CPU processing that needs to go on in your routers themselves just to manage all those peering sessions. Now, not everyone is going to want to peer with each other, but the numbers are very high. So what has happened is the internet exchange providers have provided provided a solution that helps us to scale, not the physical interconnections, because again, that's not the issue. If I have 50 providers, then I have 50 cables. That's not an issue, but it's the number of BGP peering sessions which becomes the issue. And I need those peering sessions in order to share routes amongst the service providers. So that's where this device comes into play, a root server. So a root server is like a BGP router. Okay, it exists in its own autonomous system, and it acts as a central point for BGP peering. So now, instead of, let's take the example here of ASXX and the router there. If he wants to peer with these other 4 ASs, then I have to have a peering session here, I have to have a peering session here, I have to have a peering session here, and I have to have a peering session here. And then if, ASYZ wants to peer with these other 4 ASs, similarly, they have to peer here, peer here, peer here, peer here. Okay, so that's where this high number of peering session comes from. So what the Internet Exchange providers have said, we'll provide a centralized root server here. And all you have to do, all of these service providers, all they have to do is peer with just this root server. So now, if your service provider XYZ, instead of having, 4 peering sessions or many more, if there's many more service providers you want to access yourself, now you just have one. You have one peering session with the root server. In fact, everyone has a peering session with the root server, and then you share your routes with the root server, and the root server shares your routes with all the other providers because they're all peering with it as well. So now if I have 5 providers that want to peer in this way, there are just 5 BGP peering sessions. If there are 50 BGP routers here, then instead of 1225, there are just 50 peering sessions with the root server. And so you can see how the scale is greatly improved here. So that's what root servers are, and they're a distribution point, they're a simplified way of peering in the Internet exchanges, and they provide a great deal better simplicity at scale for all of these, BGP interconnections that take place between the service providers. Now, there are these things called routing tables, and there are these things called BGP tables. So I just want to simplify this to illustrate here using the same sort of framework that we've seen before. There are 4 ASs here, and at this time I put letters on the routers. Okay, and I want to use an example here of what we mean by a BGP table and what's a routing table. What's the difference? If you're not technical, you won't know what the difference is, and there's a significant difference here. And it comes down to basically this, that all of these routers, they have these 2 tables, the BGP table and the routing table. Now, if, let's say down here, router F, okay, you can see this router F down here, it's got a local network, and he wants to announce it to everybody using BGP updates. Okay, so he'll announce it to internally to these routers here, and then these routers using peering will announce it to the upstream providers here, and then those routers will announce the routes to the upstream providers here. So eventually, all of these routers, A to G, will know about the route that was originated from router F here. And you can imagine on a bigger scale, that's exactly what happens across the network. Now, when these routers learn about this network, depending on where you are, you're going to learn about the network via a different path. So, for example, if you're router A up here, you might learn about that network that was advertised to you via this path, via F, G, H, I, and A. Or you might have learned about that route via this path, F, D, C, B, A. Or you might have learned about it, for example, via this path here. Lots of different paths to get that route to you, which means when you send your packets, you get a packet here, you can send that packet potentially down each of those different paths. But that's not really the way these routers work, and that's really not the way the internet works. And that's what we mean, and that's where these things here come into play, the BGP table and the routing table. So each of these routers that learns about this route, okay, and creates a path, they will learn about all the different ways they can send packets to get to this network down here. All of them, not just A, but all of them. They'll all learn that. And so they'll keep a record of all the possible routes that they can take. And that's what the BGP table is. It's a record of all the different paths to get to a destination. But imagine a router, that's got these 400 gigabits per second links on them, in the core of the internet. That's, 400 trillion bits per second. That is, getting close to a trillion packets per second. That's a lot of packets that they're forwarding. Now, they don't want to have any ambiguity. They don't want to sit there and say, oh, I want to use this path, I want to use that path, I want to use the other path. They want to be certain. So although they know about all the different paths, they would choose a particular path which is the best one, maybe the shortest path, or we can do some path manipulation to tell the router what is the best path. And so they put the best path into their routing table. So the difference between the BGP table and the routing table is that one has all the different paths and one has the best path. And it's this that the router uses to forward the packets. It always forwards the packets down the best path. Now, in the internet, that might change because links break and all that sort of stuff. You might have the best path 1 minute, but something might have changed. So you can then go to your BGP table and pull out another path and put that into your routing table. And that's now the best path to take. But that is essentially the difference between those in a nutshell. So hopefully that kind of makes sense. And this is going on all the time dynamically in the internet. Routers are updating each other with their updates, and that update information goes into their BGP tables. And then each router individually works out if it needs to get to a certain what is the best path is when it gets a packet. It uses its routing table to direct the packets into the right direction. Okay, so this brings us to the last term. Let's take a little bit of explanation, this one, but this last term is RPKI. So what we're going to do here is we're going to look at RPKI. We're going to see why we have it and what effectively it does to help us. So first of all, what does RPKI stand for? Well, it stands for Resource Public Key Infrastructure, which a little bit like CiDR is a bit of a mouthful. And you look at that and you think, well, I'm sorry, that doesn't really help. And, certainly in technology, we're very guilty of having, all these little phrases and acronyms. And the acronym means something to you if you use it in everyday life. But if you don't, then it can be a bit of a mystery. So here's a sort of a simplified explanation of really what RPKI is and how it helps us and why we need it. So first of all, when we say public key, what we usually mean is something to do with security. Okay, we use PKI, we use public key infrastructure when we're going to a secure website, for example. What that basically means is that there is some authentication of the website's identity. The website will have a certificate, and there will be a certificate authority that has vouched for that certificate to say that that certificate is genuine. That website you're going to is genuine, and we vouch for them. Therefore, you can feel safe when you go to that website. Well, it's pretty similar here in that respect with our PKI, because our PKI is all about authentication in terms of security. It doesn't really contain anything to do with encryption as such, but it is to do with authentication. So in our context here, our PKI is providing authentication of the roots, or let's say the origin of roots that we receive on the internet with our BGP routers running in our autonomous systems. So in other words, you put your BGP router up into the internet, you peer with someone over here, and you receive routes, not just routes that were generated from here, but routes that were passed on from here. You pass on routes, in other words, routes, as we've seen before, to get those paths across the autonomous systems in the internet hop by hop. So you send some routes, you receive some routes, and we kind of have to use those to send our packets across the internet. Now, do you recall when we were talking about BGP earlier on, we said that each internet service provider or other organization uses an autonomous system number. So, like here we have 4 autonomous systems, and each of them have a different autonomous system number. I've simplified it. It's ASN 1, 2, 3, 4. And that is a kind of a low-level way for, if you're autonomous system here, for you to know when you receive a route, let's say from this router, it's going to send its autonomous system number to you, so you know the route has come from router A, which is in autonomous system 1 here, for example. Okay, and then that gets passed on. You pass that on to your neighbor over here. So you receive the prefix. Here's the prefix. You receive the autonomous system number of the router that's advertising the prefix, as we mentioned before. And then if you're ASN2 and you pass that route on to, let's say, ASN3, then you add your ASN number in here as well. So the original ASN is sent out with the update, and you send your ASN as well to say that you're passing that route on. And then if ASN3 receives that route and wants to pass it on to router F here in ASN4, they do the same. They pass the prefix on and add their ASN3 down here. And then when the route finally arrives at ASN4, router F says, aha, this route was originated by ASN1, and these other providers are merely just passing that on to get to me. And so the administrators working for the ISP that has ASN4 can go to the internet registry and they can see who is ASN1 and satisfy themselves that they are happy to receive routes from this organization. Aha, but can they? And I say this because it's been, relatively easy for entries to be added to the Internet Registry in the past few years anyway. So is Autonomous System 1 who they say they are? And that's really where RPKI comes into fit. Perhaps what will be better than just simply announcing your ASN number is if there is some trusted organization that can vouch for ASN1 and vouch for these prefixes which ASN1 is advertising, and that therefore all these other routers can pass this route on to, where it needs to go across the internet, with some degree of faith in the, the authentication of ASN1. Some sort of authority, like a certificate authority, like we said with websites, that can vouch for ASN1 and that route. Well, that is exactly what RPKI is all about. Okay, so RPKI is a service that's provided by the Internet Registry. So here we have IANA, Internet Addressing Organization, RIPE, in this case, that's RIPE NCC, who are the European registry, and then, service providers underneath them. And this chain of authorization or chain of authority can authenticate routes. So effectively, when someone announces routes into the internet, they can register those routes with their ASN number, and a certificate can be created, and that certificate can be signed for and vouched for using a root certificate by, one of these organizations here. And so it could be issued by a service provider. It could be then vouched for by a root certificate from RIPE itself and go all the way up to, the Internet Authority. So, so they're basically providing something like you would have with, with a commercial certificate authority organization. The registries themselves are doing that. And in order to use that root authentication, there is some additional helper software called a validator. So now the authorized or authenticated routes are what we call these ROAs. So ROA stands for Root Origin Authorization. Okay, effectively, it's a prefix with the originating AS and a mask length, okay, or varying length masks here. And what that basically says is that if this ROA has been issued by the Internet Registry based on the ISP that's originating this route, has gone and registered it, they provide a certificate to vouch for this particular prefix. It can be IP version 4 or IP version 6. When your router now receives a prefix advertised to you by another ISP, before you can trust it, you can go and query, your router can go and query this validator software. And they, of course, will query the Internet Registry to see if that route is vouched for, if there's an ROA which is vouched for that route. And they can respond in 3 different ways. They can say, yeah, it's good, it's vouched for, no, it's bad, or C, it's unknown. So not everyone has obviously got to the point of registering their routes. And so there are some unknowns. In other words, there is no record of that route in the authority. But the idea is that your router can decide what to do with that if that happens. You can either accept it and trust it anyway, or you can reject it. And if you don't keep the root, it doesn't go in your BGP table and you don't use it for routing. So that root doesn't kind of poison the internet and your routing infrastructure. And so I think that really concludes what I wanted to say about RPKI. Hopefully that makes sense to you. There's a link on here, and the idea of the link here was to just provide a reference to what is the sort of latest. So you can go to labs.ripe.net and you can do a search on RPKI just to see how many routes in the internet have ROAs and are vouched for. I think it's over 50% now, but it is increasing at a good steady rate. So people are gradually getting around to getting their routes validated, but it's by no means complete yet. And that's it. That's our journey. We've got to the end and we've covered all of those BGP buzzwords in our 2 hours that we had. I hope that was digestible. I hope it was interesting. I thank you for attending. And I just leave it open for any final questions if you have any before we wrap up today.